Hello everyone, welcome to the TechGig Leaders Circle webinar on mastering real-time data streaming with Apache Kafka. I'm your host Aditya. Thank you for joining the session today. Today's session will guide you through the growing importance of real-time data streaming in enabling instant intelligent decision making for modern business needs. With a focus on Apache Kafka and Apache Flink, we'll explore how these powerful frameworks support data and AI applications at scale. The session will highlight how streaming data can be enriched and transformed to drive timely AI predictions, the critical role of the data streaming engineer, and how adopting the shift left architecture pattern enhances data quality and enables more accurate business insights in the age of AI and generative AI. And to facilitate the session, folks, please join me in welcoming Mr. Diptiman Raichaudhuri, who is currently staff developer advocate at Confluent. Diptiman is an experienced IT professional with over 20 years in the industry, having worked with both Indian MNCs and global product companies. As mentioned, he is currently a staff developer advocate at Confluent. Diptiman has also led the design and implementation of modern data platforms for large-scale enterprise applications. He enjoys working at the crossroads of data technologies like Kafka, Flink, Spark, Kinesis, Redshift, Iceberg, Glue, Hive, Neo4j, Neptune, and AI tools such as LLMs, PyTorch, SageMaker, Vertex AI, Kubeflow, especially at cloud scale using AWS and Google Cloud. All right, so now I would like to inform the audience that this session is scheduled for an hour. The first 45 minutes, our guest speaker will share the concepts through a presentation, and the remaining 15 minutes will be given to you to ask your questions. So please feel free to drop in your questions in the chat window. And now, without much ado, let's take this discussion forward. Over to you, Deep.
Thank you very much, Aditya. Hope you can hear me, see me all right?
Yes, I can hear you. I can see you
Okay.
totally fine.
Okay, perfect. So I'll just quickly turn off my video to preserve bandwidth and move to the presentation.
Sure.
Can you confirm if you can see my screen?
Yes, I can see your screen. Yes, perfect.
Okay. So hello and good afternoon. Glad to be part of the speaker session for TechGig Leader Circle. Today we are going to explore how to master real-time data streaming with technologies like Apache Kafka. And I'll also touch upon Apache Flink as a stream processor. I'm Diptiman. I'm a staff developer advocate with Confluent. And that's my LinkedIn ID on the QR code that you see. Happy to get connected as well. But uh, as Aditya has mentioned, my talk would be around 35 to 40 minutes, and then we'll take on questions. So let's dive right in. So we start with the concept of why you need data streaming at all. So why you need data streaming in the first place. So data streaming has become an essential part of every modern infrastructure. Now the question is, how does it help to set your data in motion across enterprises? And the primary reason for that is software. And software is changing every aspect of our lives. Every industry is being disrupted today. Customer experiences are being completely reimagined. Think about go back 15 years, 10, 15 years when we used to call taxis for cab booking, etc. Now, today, we always do cab booking on our app, get the notifications instantly. Buying online is changing the way we go shopping as well. So, gone are the days of waiting in long lines at your local bank to get a bank service. So the point is every company is shifting to this digital first paradigm and they're completely reinventing their business model. Today, what is happening is every business is becoming the software. So delivering the expectations that customers would have today requires a new way of thinking. So in the past, software was used to improve productivity, right? Look back a decade ago, depositing a check in a bank would probably require going into a branch, working with a ATM teller banker who would ask for your identity and all those things, right? Today, depositing a check simply requires opening an app, signing into your account, taking a picture, and clicking deposit, right? So, what has happened is these slow moving processes or workflows which were slow has been replaced by faster workflows. So, siloed businesses are becoming connected more and more. And what is fueling all this is the data. The idea of getting more data from all these operations is nothing new. And in recent years, I would doubt anyone would argue that maximizing the value of their data is critical to getting a competitive advantage. So, whether it's gaining a rich view of your customers' buying habits so their experiences could be more personalized, or validating the transaction, whether it's a fraud or not, is all happening in real time today. But even then, with software becoming business and data being the fuel driving this revolution, I still hear from businesses and enterprise continuously and regularly that it is still very difficult to integrate data and analytics within the business. It's much harder than it normally should be. And a large part of the issue is the fractured and siloed nature of the data estate, right? So when I say data estate, I actually mean these two locations for data, the operational estate and the analytical estate. So if you look at the state of things, maybe from the last 10 or 15 years, you would see that data mostly existed in these two popular locations, right? On the one side, you had your operational estate, which really existed to serve the transactional and real-time systems that ran the business, like things like payment processing, inventory processing, billing systems, on your social media, getting an instantaneous like, etc. And on the other side, you have your analytical estate, which is post facto analysis, after the fact analysis, and business decision making. And you would typically employ a mishmash of both approaches when you're actually building a data platform, right? Now, as data needs multiplied, what happened was there was this explosion of new technologies, right? In the operational estate, we had new SaaS applications, new cloud services, microservices for um, microservices for applications which were running, all the while maintaining an on-prem or legacy footprint. And you still had to wire all these applications together, integrate all these applications together to meet the expectations of your customer. And that same complexity manifested on the analytical estate as well. You were still trying to bring data from multiple different sources. So there would have been multiple different pipelines which would feed data into the analytical estate, and which created this complex mesh of applications both on operational state and the analytical estate. So, just to give you an example, if let's say your shipping system has broken or it's gone down, you don't just want the dashboard to turn suddenly red. You would also want to proactively reach to your customer, reprioritize your shipping, and update the shipping time on your website so that the user experience remains good. Now, what has happened is both this operational estate and this analytical estate connected through a mesh of batch systems or messaging middleware or maybe APIs as well has grown beyond complexity and is created this giant mess. So now let's say we take a small example of an application change, and that becomes a huge job. The schema drifts, data changes from expectations, all the applications and systems that dependent on this data are also going to break, right? But the point is, does this stop us from building applications or software? No. So one by one, all our projects would go on. These projects would come in from the ground, the requirements, and our teams would build all these customer facing applications, business operations, even Gen AI experiences on top of this messy data architecture. So these are the problems that we see what has happened in the application development and the data integration as well as the data platform space, right? So The impetus behind setting this straight is to bring in this new paradigm that we call as data streaming platforms. This improves data accessibility and help make better use of data. So data streaming is a fundamentally different paradigm that makes data as a first class citizen. Here, data is not static or passive, it's continuously evolving, like a login event, like a point of sale happening at a retail store, a customer experience happening on an e-commerce website, a trade happening on a stock trading website. And these events would pass through this continuum to the right hand side on the rich front end of customer experiences, or real-time backend operations which would analyze and investigate and do something on its behalf. So the fundamental notion is that data is moving, not sitting at rest, waiting to be queried. So data streaming enables the real-time data flow throughout a business. Just a quick check, Aditya, am I still visible and audible?
Yes, yes. I think everything's fine. You're
Okay,
still audible.
perfect. So now that we understand what data streaming is, let's put some more thought into how you could build a central nervous system, which we call as a data streaming platform, right? So with data streaming, we have built a real-time central nervous system from for the data. So be it the apps that want to exchange data, be it the change logs, the CDCs that's coming from databases that can be onboarded onto this data streaming platform and then loaded into the analytical estate, right? So in order to do that, what we really need to understand is we need to shift our thinking from a tightly coupled point to point integration kind of a framework to a multiple subscriber decoupled architecture, where the data wrangling, the data quality check, the value of data is not only um, calculated downstream, but it is producer presented, governed, and reusable. So the source becomes the cleaner of the data. So the data that is received on downstream is absolutely pristine and pure and cleaned. So instead of writing point in time queries on static data, we can get cleaned and cleaned and data quality validated data for continuous processing at generation time, right? So that's the motive behind why would you need a data streaming platform at all, why you need data streaming, what does it help uh, having this having this clean data at source and a data continuum, right? So now that we understand the why bit, let's go a little deeper on the what bit of it. So what is a data streaming platform? So data streaming platform, if we take the very basic capabilities, although I have a slide which talks about the capabilities a little deeper, but then it actually revolves around this trinity of data streaming. I want a producer which would publish streams of events. I would have a consumer which would subscribe to for this stream of events. There would be a broker which would store these streams, and then there would be a stream processor where we would apply sophisticated processing technologies like deduplication, like null value removal, like entity resolution, like finding out patterns whether a transaction is fraudulent or not. So these analysis. So it revolves around this three broad blocks, right? So there would be a producer, there would be a publish subscribe from the producer and the consumer, storage of the streams, and analyzing these streams, right? So essentially, what needs to happen is we need to happen a construct, an architectural construct, which enables us to get these events, get this streaming data right from the newest on the right hand side to the earliest, which could be termed as historical data, and everything should be available on the time continuum. So records need to be modeled as events with a timestamp, and when these events are published, they would be stored in systems like Apache Kafka, which is a stream storage, event streaming storage framework. And these would be written sequentially and immutably. Immutably means the records will not be changed, so that you could do replay, and for all the legal and data privacy purposes, you would be able to access those data as well, right? So this grows on unbounded, right? So when new data comes in, it gets appended to the end. It's a sequential write, and then consumers subscribe to this construct, which we call as Apache Kafka topics. I'll go deeper into what an Apache Kafka topic is later. But then, just as a starting point, these data are stored into Apache Kafka topics. Just like a table in a relational database, an Apache Kafka topic is a namespace constraint storage of a specific kind of streaming data. It could be an orders data, it could be sell data, it could be customer experience clickstream data from an e-commerce website, it could be sensor data coming from IoTs, etc. Right? So data writes would happen as append only writes, and records would be immutable. And this single immutable log structure provides this shared narrative for all consumers in an organizations through Apache Kafka, right? Now, then, what would be these events? As I told, these events could be events that are happening in a business or an organization or within a thing. So, for transportation here, the events could be sensor measurements from vehicles that you want to analyze in real time in order to warn about malfunctions, like predictive maintenance. Your brake shoe is maybe failing, your clutch is failing, and stuff like that. For banking, events could be the individual transactions that's being created by customers. This would be stored on Kafka, so that um, there would be sophisticated applications which would analyze the trend of applications and then figure out whether it's a fraudulent applications or not, right? Now, this is just to tell a story. You look at this event, which is nothing but a JSON structure, and what you would see is not all events have to be, very very high velocity, high volume. They could represent a specific analysis from a human perspective as well, right? So look at this. On 1970, this QXYZ airport was an unimportant tiny airport, but in 2020, you see, it is still not very big. But then it did get some more markings like this ILS1 and type super um, and status active. So it went from absolutely tiny and non-active, inactive to active. And then today in 2020, you see it has grown its runway. It's covered with a surface. So you get the event where you understand that something else has happened. So it actually showcases the change in time of this specific entity, right? So now the point is, all this is powered by Apache Kafka. So Apache Kafka is the backbone of the central nervous system for processing these events. So be it a shipment, be it a customer experience, Apache Kafka stores these events, and then consumers can read these events in order, and then create the backend for these real-time streaming data. So essentially, what we want to build are topics, these Kafka topics, which matches and aligns to the business. So we in financial services, we could have customer topics, account topics, web logging topics, etc. For transportation, we could have Apache Kafka topics like vehicle telemetry drivers, etc., etc. Right. So what would happen is these topics would become your data products and could be used as a reusable data assets. And if we do that, what we end up with is, in our terminology, we call a data flywheel by reusing these data products. So we could actually build newer data products and newer data applications. Let's say with purchase, let's say with payment service and mainframe data, we could create something like an inventory and payments and customer, and create watch leads and profile management, etc., where we could combine multiple topics, multiple streaming data sources, and build sophisticated applications around it, right? So this is another example, right? So we could take accounts topic, web logins topic, customers topic, and transactions topics, keep on analyzing the data, streaming data coming from these, and we could build a fraud detection application around it. So these data products as topics would give rise to newer business use cases for the organization. So Confluent Cloud provides a data streaming platform with Apache Kafka and Apache Flink as the backbone. And let's now quickly analyze what are the capabilities of this data streaming platform, as we call it, and how Apache Kafka and Apache Flink comes into being, right? So, when we talk about capabilities of a data streaming platform, we would focus on broadly four broad categories, which would be stream, which is done by Apache Kafka, the connect, which would be done by Apache Kafka connectors, govern, which is normally done by a schema registry, which typifies the kind of events that passing through the system, and then processing through something like Apache Flink. So let's quickly jump and understand what these four broad categories are. So we start with the streaming aspect, which is Apache Kafka. So as I told you, Apache Kafka topics are the categories used to organize events. So events which Kafka manages have a tendency to proliferate. So Kafka's fundamental unit of organizing these events would be a topic. And if you have never heard of a topic before, what you can think of it is being something like a table, as I told you, in a relational database. It's got a name, it's got a container. And as a developer using Kafka, when you actually start writing code against this topic, it is the only unit of abstraction where you produce your data. So topics are sometimes referred to as log of events as well, because it within something known as a partition, which is like a broken down versions of topics, you would have events which are sequentially ordered. But then broadly, topics are the categories used to organize similar kind of events. Now we go a level deeper into partitions. So Kafka partitions within a topic, horizontally scale these topics and makes it linearly scalable. So a partition divides a Kafka topic, into multiple parallel event streams, each of which is stored on separate Kafka brokers and can be consumed independently. So you get the drift, right? So we want to create a linearly scalable architecture where my topics could horizontally scale as much as I want. My consumers can be added as many as I want because my topics would reside on different brokers or servers, right? And making sure that these topics are actually stored in different brokers or servers introduces the fault tolerance and reliability, because topics are copied and kept a backup of these topics are kept a backup within these other brokers, right? So what happens is this replication is implemented at the partition level. So each partition would usually have end up having more than one or more replicas, which actually means these messages would be replicated over to multiple brokers. So in case one broker goes down, you would still be able to get the data from other brokers, right? So now let's understand what a consumer is. A consumer is a regular microservice, to be honest. A consumer is just an application that processes, that reads messages from Kafka topics. You could have one consumer, you could have multiple consumers, you could group consumers and behave in a way that an entire group is behaving. Um, and then what happens is this producer, consumer, and broker together gives rise to this linearly scalable architecture. So if I want to produce more, I have more data to produce. I would go on and keep on adding producers. If I want to store more data, I would horizontally scale brokers, because anyway, my topics and in turn my partitions are copied and replicated over other servers. And I could add more consumers if I want my consumption speed to increase, right? So that's a very basic understanding of how Apache Kafka works. And what you understand is by streaming, I would get these messages or events into my broker in my partition, and my consumer can run an infinite loop and keep on consuming. Right now, let's focus on the next section, which is connect. Right. So with connect, Confluent Cloud has greater than 100 plus managed connectors, as well as you could bring your own connector by building your connector using the open source Connect API. And users would provide these connector plugins and to the data streaming platform. Teams can bring and upload Kafka Connect plugins from any source, uh, custom connectors built using the Kafka Connect API and SDK. So once you uploaded your connector, you'll be able to find it on the connectors page, and then you would be able to create sources and syncs and connect to the data streaming platform. So essentially, what would happen is all these connectors would connect your sources to the data streaming platform, powered by Confluent Cloud or Apache Kafka, and it would also create connectors for your syncs. And this is just a representative example of many connectors, popular connectors that we have, right? Now, from an architecture perspective, what happens is there are connect workers which does this copying of messages from the source to the data streaming platform, and from the data streaming platform or the broker to the sync. So these are auto balanced across workers. Failures are automatically handled by redistributing work, and you can easily scale up the cluster up and down by adding more workers with it, right? So Kafka Connect does not own the process management at all. So what happens is we don't want to make assumptions about using Mesos or Yarn or Kubernetes, but Kafka Connect will work out of the box in any of these cluster management systems. So your auto scaling and auto balancing, etc., could be supported over all platforms. So Connect, as we understand, connects the sources and the syncs with the data streaming platform with Apache Kafka. Now let's focus on the govern. The govern bit is the schema registry. As I told you, the schema which provides a common language to enable producers and consumers and platform teams to work in harmony, right? So what happens is while I'm sending these events from the producer, I would impose a schema on top of it, a type on top of it, and my broker would be aware that a schema is sorry, a schema is imposed on this topic. And in case there are events or messages which do not comply with this schema, they would be transferred to a new topic, let's say a dead letter queue. Similarly, the consumer apps would also enforce the schematization of these messages when consumers read it, when consumers deserialize the message on their bit, right? So what happens is once I have this schema, I could actually create like this tree of metadata for within a topic, right? So I could have an cluster in Confluent Cloud running Apache Kafka brokers. I could have a topic. I could have connectors, but then the entire ecosystem would be bound with the schemas that we have provided. Now, schemas also provide a very important part of a modern data platform, which is data quality. So within a schema, we could also add data quality rules. And by data quality rules, I mean rules like this. So if you look at this rule, what is happening is I'm just checking if an IoT sensor event device temperature is greater than 25 or not. If it is greater than 25, the event fails to be loaded to the broker, it reaches a dead letter queue. And I could check the dead letter queue in certain sequences and understand what are the bad devices which are throwing these rules. So these rules could be either something like a conditional rule, or it could also transform a specific field within a schema. So these kind of rules could be appended within a schema as domain rules, which enforces the data quality checks and introduces something which we call as a shift left architecture, where we do the data cleansing and data quality checks, etc., right on the source even before it reaches the downstream analytical estate, right? So what happens is while serialization, these rules it gets invoked, and if the message does not follow a schema, it goes to a bad device topic, which gives rise to this shift left architecture. So with all these heterogeneous sources, what happens is there is very little check possible to be done on the transaction processing side. So we take this raw data streams within the data streaming platform within Kafka, impose these schema checks and data quality checks, and curate data products by having by combining multiple data streams and applying those data quality checks, and then we push these data onto the analytical estates, whether it's a business application, whether it's a lake house, whether it's a data warehouse, etc., etc. Right. Now let's quickly focus on the last pillar, which is process. I hope I'm doing right on time, right, Aditya?
Yes, absolutely.
Okay, perfect. So let's focus on the last bit, which is processing, right? Which is where Apache Flink comes in. Apache Flink is the stream processor of choice that we normally use. So stream processing acts as the compute on the data that's getting stored on Apache Kafka. So what happens is we push this data through producers to Kafka topics. Flink acts as a stream processor, and it creates and run those string applications just in time, and then get the data to another Kafka topic so that the consumption could be done from this new topic. And this data is now deduplicated, cleaned, enriched, etc. Right? So processing data at ingest, as I told you, at source, it is important to have clean and enriched data as close to its generation. Not only does your first pipeline gets the benefit of being real time, but it also reflects the current state of your business. So we could do your processing once through Flink, and then we could do it right, and then pass the message on to the data warehouse, right? Or your database or your SaaS applications, etc. So what are the capabilities that Apache Flink provides? So Apache Flink provides filtering, real-time processing, data deduplication. It could reroute. We could actually join different Kafka topics and then create an enriched topic with both these joined data. And applying this would eventually give rise to topics which are absolutely clean, ready for consumption, right? So essentially, we could write Flink SQL, and with Flink SQL, we could create such kind of joins. So here, this is a small example where I've joined the currency rate and orders, and I've created a new Kafka topic which actually has both. So data transformation, streaming joins, lookup joins, fan out queries are some of these capability for Apache Flink. And what we could also do is we could also apply sophisticated aggregations based on time. So this is an example where I'm trying to group by account all the transactions that's happening. And then for each transaction, I want to do a summation based on, let's say, last hour or last 15 minutes, or maybe last one day. I want to see the summation of all transactions just to ensure that there is no fraudulent applications taking place, right? So essentially, what how Flink works is I have my Kafka topic, all the streaming data is coming in. So here it is, let's say an e-commerce user click stream which is coming in, and I would apply an aggregation where I want to see the top users, right? So I would want to select the user and the count of this user, how active this user is from this table, and then push this data into another topic. And this topic could be consumed by a microservices downstream to figure out if somebody is a top user, whether I would go for giving a promotion. And these are very simply done with Flink, and you could run these Flink jobs right on Kafka topics just in time, and the entire thing would happen on real time, right? So essentially, what happens is we get everything, all of this, and the idea is to deploy the fully managed Flink service along with Kafka topics, along with the schema governance tools, being cloud agnostic on a data platform. So that's the Confluent Cloud data streaming platform, which you can run on any cloud. And then you get the benefit of the security, governance, monitoring, the connectors, as well as the power of Apache Kafka and Apache Flink. Very loosely, this is how it looks like. So you would have sources of data, which could be logs, which could be databases, custom apps. There would be Kafka connectors, which would connect your source with the Confluent data streaming platform. Apache Kafka would store all these records as immutable logs, and we would apply the schema registry for cataloging, for stream lineage, for data quality checks, and Flink would apply the processing on top of these topics by enriching these topics, transforming this data, and then we could either publish it as a stream for downstream microservices or online transaction kind of applications, or we could push it to a data warehouse, or as we have just released a new product called Tableflow, where these Kafka topics could be presented or materialized as iceberg tables, for consumption, subsequent consumption by these query engines. So these three would be the how the transform topics or the data products, as I showed you, would actually be how it would be connected with the analytical estate. And the data streaming platform would apply and create all this magic so that you shift left and you create a data which is pristine, which is clean, and with all data quality checks passed, right? So if we want to build it piece by piece, this would be the piece where Apache Kafka and Flink would store the stream and then process the stream to make it more transformational, to make it more clean, make it deduplicated. We would have our legacy data systems, any kind of applications which would get the data through Kafka Connect, and then we would be using Kafka Connect to create sinks and then push this data into all these sinks. And then we would have this schema registry to have a governance layer on top of it, and we would build it on any cloud, AWS, Google Cloud, or Azure. So a couple of quick use cases that we have done locally. So Misho is one, and it's a public use case. You can read it on Google. Swiggy is another one, which is heavily using Confluent Cloud Data Streaming Platform for imposing governance and the metrics around data, which is very important in today's world. And then Mobile Premier League, where they're using Confluent Cloud to bring out critical data insights. So that's it. That's all that I have. I think I've finished 4 minutes early. Um, but I'm ready for any questions now, and I'll quickly just stop my presentation.
I think thank you for the insightful presentation, Diptiman. We have received some interesting questions from the audience. Let's take them up. They are available in the question panel.
Oh yes. So Manoj Mohan asks, do we have transcripts enabled for this session?
Okay, I'll answer that. Yes, the entire session will be recorded, is being recorded, and will be live post the we complete the webinar. Now you can take it.
Okay, all right. So Sharad Oza asks, if we are putting these events in a queue, how do we say it is real-time data processing? I mean, it will be picked up by consumer application for processing when any consumer will be available. Yes, so the design motive is to have this data available for processing in real time. So the producer produces this event and it goes to the broker. It reaches the topic partition, and then if you have your consumer available, you would be able to process it real time. If you don't want to process it real time, it would become stale, of course, but the event does not go away. So you would be able to run it. Just one small minor correction which I would try to make is it's not a queue, as I mentioned earlier. It's a publish subscribe kind of a reference architecture. So what happens is the moment the event is published, if my consumer subscribes to the topic within Kafka, I would immediately be able to process this data. So consumers normally run in an endless for loop or a while loop, and it keeps on checking the partition whether any new message has arrived or not. The moment a new message arrives, the consumer poll would pick it up and then pass it along the downstream application chain. So then there is another question from Aditya Tiwari. If you have any questions, oh, okay, I'm sorry, that's you. Then another question from Mahesh Kaushik. How do Kafka and Flink complement each other in a modern real-time data architecture? Can you share a typical architecture where both are used together? I think I showed you one where we have a Kafka topic of user clicks, which is the clickstream events coming from an e-commerce website. So what happens is the Kafka topic keeps on getting these messages and events one after the other. What Flink does is whenever the event arrives, based on the time window, so Flink has this windowing, no, the notions of windows, which is temporal sections or time bound sections within a stream. So let's say I want to see how many users have clicked page A in the last 30 minutes. So what Flink would do is it would process the result and then apply the SQL, get the result out, and then push it to another topic so that the other topic, the resultant topic, would have absolutely fresh insights of how many users are doing it. So that's how normally it works. You keep on pushing data onto Kafka topics, run your Flink jobs so that the Flink job can get this data, join this data, transform this data, and put the result in another topic in real time, and your downstream application would be able to pick it up from there. There's another question from Parth Consul. What are some best practices for enriching and transforming streaming data before it's used for AIML predictions? Good one. Um, so it's actually interesting you asked this question. So Kafka and Flink today it's being used the most for AIML applications, believe me or not. So I just came back from Kafka Summit London and I did a presentation I presented my paper on Flink, on Python Flink. And um, OpenAI presented a paper on Python Flink just before my paper. Um, and they actually talked about how Flink enables them to get these millions and billions of data events pass through Flink and then pass it through their AIML, MLOps kind of systems. So what essentially happens is Flink lets you clean out this data, right? So all the deduplications, all the null value removals, which are very, very important. You can convert data into embeddings if you want today. Modern Flink has all these capabilities. So I can pass in just a text-based event and modern Flink can take it and then give me back an embedding of this data and then push it into another topic, right? So all these happens, all these are good data cleaning practices for AIML predictions, null value removals, duplicate value removals, aggregations, doing counts, creating embeddings and stuff like that. So Flink is very, very well equipped in terms of handling that. Let's take another one from Vansh Kataria. And Vansh asks, how does Flink handle stateful computations at scale, and what are some challenges you face with state management in real-time pipelines? So with Flink, the open source Flink, as I mean, state is managed and stored by something known as a RocksDB. So RocksDB is the framework for managing state. And if I run a stateful computation, a very simple example is the one that I showed you. Select user comma count from the user clicks and group by user, right? The moment I do a group by user, what happens is based on that last 30-minute or whatever is the duration on which I want to run my query, it needs to keep the state, right? So for Flink, it becomes extremely important to understand how, when I'm doing, let's say, a join, how the tables which are participating in the join, the build side and the probe side, would actually increase in state, right? So if I have a duration which is pretty long and the velocity of events is very, very high, then state grows very fast. But if it is not the case, then state does not grow very fast, right? So today, what Flink does is Flink takes a balanced approach and it does all these things under the hood. So you don't really need to poke and do stuff with RocksDB, to be honest. But then there are newer disaggregated state um, Flink improvement plans which have started floating around, where people are thinking that if we could shift the state from in memory and disk to, let's say, something like an S3, maybe the latency would increase, but then the problem with state explosion would go away. So all these things are happening. But by and large, what I've seen is if you're running your job, let's say on Confluent Cloud, this happens under the hood. and Flink actually manages state, and it increases its resources in case the state would tend to increase beyond a certain point. You could also apply stuff like state TTLs, time to lives, where you you restrict a state to grow beyond a certain point, and if the time to live exceeds, the state gets cleaned up or purged. Okay, so oh my, sorry, I missed it. So we went till Vansh Kataria. Then we have Tobias. Real time has different definitions. It can mean live, like watching a sports game. Frequently, it has multi-second delays, but that's fine. Real time can also mean at the time. What kind of real time does Kafka support? So, Kafka supports. I would say both, because if I dissect a Kafka message at the broker, what I would see is the message would be imprinted with the created time, as well as any processing that we do on the message or the event on this Kafka, the message. I would actually add the log append time, right, which is the server processing time. So we do have a choice of whether we want to do our processing based on event creation time or event time, or the log append time, or which is the processing time of the server, right? So you do have a choice. But then you get to understand that with Kafka you can achieve single digit millisecond latencies as well. It's not unheard of. We have seen infrastructure where single digit millisecond message processing is around. But at the same time, modern Kafka practices, like warp stream, let's say for example, also lets you store your messages not on disks but on S3 directly, where the TAT or the turnaround time increases a little bit. If you are on, let's say, S3 Express Zone, it would border around 900 millisecond to a second. But then, if cost is not, if cost is a top priority parameter within your infrastructural decisions, you could go for that. But otherwise, Kafka would support single digit milliseconds at scale. Then we have Raghavendra, who is asking, can we get this slide deck post presentation? Definitely, I would share it with Aditya, and Aditya can share it. I hope that's right, Aditya. Right?
Yes, that's perfectly fine.
That's
What do you think?
perfectly fine. We have, how are we doing on time? So we still have time. So we have one from Sapana. What skills and tools should a data streaming engineer focus on to remain relevant in the AI driven data landscape? So I would say definitely Apache Kafka, Apache Flink. You got to have a very good understanding of SQL and Python. So SQL and Python both you should study, because if you study Python and SQL, you would be able to handle both Apache Kafka and Apache Flink, because we don't really want to go directly into the internals of Kafka. Kafka has more than 800 plus knobs and configurations which you can use to ensure that you have a scalable infrastructure. And if you're running things on something like Confluent Cloud, which hosts Kafka and Flink for you, all you need to do is run your SQL and your Python jobs. And what I understand is if you are good at Python, I don't think you would have any problem linking to the AIML space as well. So what we see, how we perceive the future is all these microservices would slowly become AI agents, to be honest. So today microservices are reading from Kafka topics. Tomorrow these would be agents which would either use MCPs or call these consumers and then pass this data along to, let's say, an A2A or an agent to agent kind of a framework, and then let the agent take over. So I think if you're on SQL and Python, you would have a fairly good ground um, for understanding Apache Kafka, Apache Flink, and then lean on to AIML. Then we have one from Keval, which is how do you ensure data consistency and reliability in high throughput streaming applications with Kafka and Flink? So Kafka support. So let's break it down. Let's talk about data consistency first. So for consistency, you have the choice of the Kafka semantics, which gives you at exactly once semantics or at least once semantics. With at least once, of course, the pressure and load on the Kafka systems would be a little less, but at the cost of duplicate messages. So there could be stages, network failures, and there are all those specific failure modes. I don't want to go through those detail. You can Google it. um, with at least once, but with exactly once, which is normally implemented through something known as idempotent producer and the transactions API within Kafka, you can get data consistencies at the highest possible level. So you would get exactly once data delivery with no deduplication, and brokers would abort the transaction if the exactly one semantics is not held. Reliability is an easier answer. It's reliable because of the replication structure that Kafka has. So if you have your topics replicated, your if you have a replication factor of, let's say, 3, you are bound to have a quorum which would give you fault tolerant systems and reliable systems. So even if your nodes go down, you would still be able to extract data, and it's reliable. So reliability is bolted on. So it's a batteries included kind of a thing for Kafka. But for data consistency, you have these two choices. So you could either have an at least once or an exactly once kind of a semantics to do that. Then we have Pania Kapoor asking, how does Kafka handle data retention? So by default, data retention is 7 days, but then there is a configuration called retention.ms, and you could change the configuration. You could retain it for a much smaller duration if you wish. And then, of course, there's another thing called the compaction policy. So you could have a compaction policy of either delete or compact. So if it is delete, what happens is the partition gets purged. If it's compact, what happens is, if your Kafka message has a key, the compaction job actually keeps the key with the latest key with the value, and any other messages with the same key with other values are purged. And of course, when I say purged, the purging process or deletion of a message in Kafka is a little nuanced, to be honest. So what happens is we actually put a tombstone marker. So if you're consuming, you will not be able to consume the message, but the message would actually stay, and there would be a background job, a background thread, which would pick these tombstone messages up and then purge it on its own. So that's how Kafka handles data retention. Wow, I think, yeah, I think I've gone through all.
I think we have come towards the end of the session. Yes, thank you so much, Diptiman, for this truly empowering and motivating session today. It was an absolute pleasure having you with us. I would also like to thank all our wonderful participants for their enthusiastic engagement and for making this webinar a great success. But before we wrap up, I would love to hear your thoughts, Diptiman, on our initiative, TechGig Leaders Circle, and what do you think about its mission to connect tech leaders and drive meaningful conversations in the developer ecosystem?
I think it's fantastic. It's wonderful to see this kind of mission that you are running. So the Tech Gig Leader Circle actually brings in all these like-minded professionals and enthusiasts and engineers together. And I'm absolutely delighted that I got a scope to talk and present my session at Tech Gig Leader Circle. And I just hope that this continues and proliferates, and more such events happen. I'm absolutely thankful to Tech Geek Leader Circle. You're doing a great job.
All right, that's great. Thank you once again. And I would again like to inform the audience that this session has been recorded, and the recording will be soon available on our site, techgeek.com, and Leader Circle website. So you can find it there as well. For now, yes, thank you everyone for joining us, and thank you so much, Deeptiman, for doing this session.
Thank you. My pleasure. Take care. Bye.